So we're going to move into section 9.1, where we're going to test hypothesis of two population proportions. Now, kind of like all our hypothesis tests, we're going to start out with some assumptions. And the assumptions in this case are that you have independent samples. And then the second part is that the number of successes and number of failures is 5 for each. So you have to have at least 5 successes and at least 5 failures in each of your samples. I believe statdisk will give you an error if this assumption is not met, and you'll have to do something else to test things in that case. Now, the first part of my job here is to help acquaint you with a lot of notation. And to that end, we're going to actually start with example B. Before we get there, let me give you a heads up as to what to expect. A lot of this is just your basic hypothesis test, where you're going to state your null and alternative hypothesis in step 1, step 2, decide on alpha. Step 3, and I've kind of updated my handout here for you, is to enter your data or summary statistics into statdisk and even tell you where to go: analysis, hypothesis test, proportion to sample. It's that, or you can spend time finding the critical values from the Z distribution and testing things in a classic way. But we're not going to do a classic way. We're using what's called the p-value approach. So step 4 is just to find the p-value. That comes from the software that you use or your graphing calculator or similar. If the p-value is less than alpha, then reject, and then state your conclusion in words. Now, along the way, there's a lot of little things we need to figure out, like x1 and n1, x2 and n2, and then this thing here, p hat pooled. So we're going to do that with example 1. It's going to be example B, which is right here. Now, it's unfortunate that this is another one of those problems where they stripped away anything interesting about it. In a large clinical trial, 393,249 children were randomly assigned to 2 groups. The treatment group consisted of 196,786 children given a vaccine for a certain disease, and 27 of them developed the disease. The other 196,463 were given a placebo, and 104 of those children developed the disease. So consider the vaccine group to be the first, consider the vaccine treatment group to be the first sample, identify all these things, N1, P1 hat, Q1 hat, N2, etc. So a lot of the things you need to figure out. So let me start by sharing with you my screen as to what I'm going to be writing down. I still want to write down X1 and N1, and then P hat 1. Now X1 is going to come from our first sample. So kind of reading this and treating this in order, I've written things here in blue. Now there's 2 numbers in blue. There's the large one and the small one. Which one do you think is going to be my X1 and which one do you think is going to be my N1?
Large
N1 would be bigger.
The large one's going to be which one, X1 or N1?
N1.
N1, good. So it's going to be 196,768, or 86, how about that? And then X1 is going to be 27. And that gives me P1, which is 27 divided by 196,786. If you take out a calculator, you can calculate that probability is 0.0001372. Let's cut over here to example 2, or sample 2. The other 196,463 children were given a placebo, and 104 of those developed the disease. So, okay. So something like this, 104 out of the 196,463. So that means p hat 2 is 104 divided by 196,463. And that gives you a probability of the disease of 0.00052,936. So either way, is your chance of getting the disease small or large?
Looks very small.
Looks very small in both cases. All right. There's one last thing that we need, which is Q hat. Someone tell me how I'm going to find Q hat. Think back to what we did with our binomial probabilities.
1 minus p.
Yep. So 1 minus P1 hat, which is going to give me 0.9998628 here. And 1 minus P hat 2, which is going to be 0.9994764 here. So that's just a lot of notation. Now there is actually one more little bit of notation that I have to introduce. On my handout, I write it differently than the book does. They use P bar. P bar for them is x1 plus x2 over n1 plus n2. It's like an average between the two groups of, well, what's the overall rate of getting the disease? The average rate of getting the disease between the two. And so for this case, it's 27 plus 104 divided by 196,786 plus 196,463. That gives a total of 131,393. Excuse me, 131 over 393,249. There we go. So even the average is still pretty small. Anyone want to take a stab at what Q bar is or how to find Q bar?
1 minus p bar.
Yep, perfect. 1 minus P bar, 1 minus 0.0003332. End up getting 0.99966, etc. So chances are really good that you don't get this disease, but there's also a chance that you will get it. Now the disease, if you're looking in the actual textbook, is polio. And I think they conquered polio in like the 50s and 60s. It's been mostly eradicated, but it was a devastating disease. And even though these probabilities look pretty small, when you multiply them by millions of children, it makes a big difference. So one thing that you could do in another class, not this one, is look at the ratio of these two. And if you look at the ratio of those two, then it tells you a good story about the vaccine. So let's take these two rates and divide them. This one divided by this one. So I'll do 0.00052936 divided by 0.0001372. This is called the relative risk. And basically what it says is you're almost 4 times more likely to catch polio without the vaccine as opposed to with the vaccine. So that's a significant result. You're really cutting down tremendously on the number of cases of polio with that vaccine. So it was definitely a very highly effective vaccine, and it was effective in all but eliminating polio. All right, so there's kind of like a little warm-up example. And I hope that it gets you familiar with the notation. Like I said, my notation for this P bar is a little different. I like to use P hat pooled. You know, that's just me. You don't have to use that. This is what I use. I like it because it reminds me that this is an estimate and that the subscript P here is that it's pooled. It's a pooled estimate. Okay, let's actually do some hypothesis tests, unless there's some questions about example B there. Do I actually want to finish this one up, do the hypothesis test for this one? Might as well, since we're already vested in this and we've got notation down. So actually the numbers are a little different here. And this is the problem that I run into sometimes when I refresh things, I get different numbers. We'll just use the numbers from example B and do the hypothesis test here for example A. Assume that we have a 5% significance level. We want to test a claim that the proportion, let's see, maybe we should just use these numbers here. Test a claim that P1 is less than P2. Now, a word about the notations there. A lot of times, what I'll do, instead of using subscripts P1 and P2 for the proportion in group 1 and the proportion in group 2, I like to make them a little bit more specific. So I'll use things like P sub vaccine and P sub no vaccine, or P sub V versus P sub NV, stuff like that. Let's go through the problem together. In a large clinical trial, 399,062 children were randomly assigned to 2 groups. The treatment group consisted of 198,630 children given a vaccine for polio, and 35 of those children developed the disease. The other 200,432 children were given a placebo, and 122 of those children developed the disease. Consider the vaccine treatment group to be the first sample. Completes part A through D below. All right. So it says, assume that a 5% significance level would use to test a claim that P1 is less than P2. Which is better, a hypothesis test or a confidence interval? Now, this is just a heads up. Generally speaking, a hypothesis test is going to be better. But there's a couple ways you can test that hypothesis claim. And those 3 methods would be the confidence interval method, the p-value method, and the critical value method. Of those 2, the p-value method, which is what we do, and the critical value method are going to be equivalent. So I'm giving you the answer to one of your homeworks here. The p-value method and the critical value method essentially give you the same answer. Confidence intervals, yeah, generally they'll agree with this, but if they don't, then you have to make a decision as to which one you believe. Both of those methods are based on standard deviation and the assumption that the 2 population proportions are equal. If a 5% significance level is used to test a claim that P is less than alpha, what confidence level should be used? Let's just run through the hypothesis test the way we'll do it, the way we do it in class. which is our 6 steps. So let me go back here to hypothesis test, our little handout, and start up here with the claim. HO and HA. So step 1. Let's see if this vaccine actually works. Now, if it works, then the percentage of people who get the disease given the vaccine should be less than the people who don't get the vaccine. So I'll write it like this. Probability of getting, or proportion of those who get the disease given the vaccine is less than the proportion who get the disease given that they didn't get the vaccine. Now in stat lab, it'd probably be P1 equals P2 and P1 is less than P2 is how you end up having to write it. We're going to perform this test at the 5% significance level. We should actually probably maybe even do it at the 1% significance level, but we got 5 here. That's fine. I'm sure that given the significant numbers, we'll find a difference. For step 3, we're going to need to enter in some data. So let's take stock of all the different pieces of data that we need here. And let me go back up to example A. So we've got 2 groups worth of data. We've got 198,630 children given the vaccine. 35 of them got sick. So that's your X1 is 35, N1, 198,630. N2, X2 and N2. Let me highlight those purple. Now we'll do blue. 200,432 were given the placebo, and 122 of those children got sick. So there's the information we need to pull out of the problem in order to put that into statdisk and get a p-value. So let me put this into statdisk. This time we're going to go to analysis, hypothesis testing. Which one of these 7 should I choose? So I went to analysis, hypothesis testing, but now I've got a lot of choices.
Was
Which
it the
one?
proportion 1 sample? Two samples.
Two
Sorry.
2 samples, yes. So we've got 2 samples, and we're still testing a proportion. So proportion 2 sample. Thanks for that. Our alternative hypothesis is population 1 is less than population 2. The one thing you got to be careful of is inputting the data correctly. Make sure that you keep sample 1 and sample 2 straight. So sample 1 is the data from our vaccine group. There was 35 children there that got sick out of 198,630. Sample 2 had 122 children get sick out of a sample size of 200,432. This had to be quite a logistical problem, a challenge. I mean, having 400,000 children in a study, getting all their data in, wow. The data, by the way, was analyzed at the University of Michigan, and they found it to be a very effective vaccine. Number of successes in the range must be 5 to...
Isn't X 125?
Oh, yeah, I got these in backwards. Thank you. There we go. So 35, and I assume I got these backwards as well. So let me change that to 122. That's looking better. I was gonna say, I thought we had N and N1, or excuse me, X1 and X2 were both greater than 5. Okay, cool. So what statistic do I need here? What value am I looking at?
P-value?
Yeah, and the p-value is a bunch of zeros. Wow. So that helps me out with step 5. Megan, what should I do here based on my p-value? Do I reject H naught or fail to reject H naught?
Reject.
Yeah, thanks. So reject H naught. Our p-value is less than alpha. If the p-value is low, H naught must go. So we're getting rid of that. And step 6 is your conclusion. Now, because this problem wasn't exactly written up for us, I'm going to state that our original claim is that the vaccine is effective, that the proportion of people getting polio with the vaccine is less than that proportion without the vaccine. So let's take it to our favorite handout here. This one on wording the hypothesis conclusion. Does your original claim contain the condition of equality?
No.
No. So we branch down here. Do we reject H naught?
Yeah.
Yeah. So this is how you're going to word the conclusion. The sample data support the claim that the vaccine is effective. The sample data support the claim that the vaccine is effective. And by saying is effective, I mean the proportion of people who got the disease with the vaccine is less than that proportion that didn't get the vaccine. All right. Let's do one more. Are we okay with this one? It was kind of like a spur of the moment example, but it did show you exactly what kind of things you need to work with as you're working with a hypothesis test for two population proportions.
Yeah.
Yeah.
I got a couple votes for yes. Any comments or thoughts before I move on to the next one? Okay. Let's take a look at the next one. So this one, yes. This one, was written a bunch of years ago, but it seems more relevant now. A newspaper published an article about a study in which researchers subjected laboratory gloves to stresses. Amongst 219 gloves, vinyl gloves, 66% leaked viruses. Among 219 latex gloves, 15% leaked viruses. Now, we don't have the accompanying data display to actually finish this one up. That's okay. we're still going to make a test at the 10% significance level of the claim that vinyl gloves have a greater virus leak rate than latex gloves. Now that word rate right there is kind of indicative of something that you need to pay attention to when you're doing this problem. Oftentimes when you set these things up, your hypothesis test, you're gonna be like, I don't know, what do we got here? Are we testing a mean, standard deviation, a rate or proportion? And you can kind of eliminate standard deviation. This has nothing to do with standard deviation. You do have to think a little bit more about the difference here. Are we dealing with a mean or are we dealing with a proportion? Keep in mind, proportions can be percentages, or rates. And that's exactly what we have here is a rate. The other thing to notice is that we've got two samples, right? I put one in yellow, I put one in blue. No special significance to those, just happen to be colors that I chose. So that's showing you we've got two samples. And so let me write down some data from this and get working with our hypothesis test. We're going to test the claim that the vinyl gloves have a greater virus leak rate than latex gloves. So, all right. Now, as I said just a little bit ago, I like to subscript these. So what I would write is that the rate for vinyl gloves is greater than the rate for latex gloves. Now in stat lab, you're gonna have to put P sub 1 is greater than P sub 2 and just keep track of which one's which. Okay. We'll still use these. That's our original claim. And that goes in a null hypothesis. Well, actually, something goes in a null hypothesis. Where does this one go?
Alternate.
Yeah, that's going to be the alternative hypothesis that leak rate for vinyl gloves is greater than the leak rate for latex gloves. Thank you. Somebody tell me what we're going to put in HO.
PV is less than or equal to PL.
Thank you. PV is less than or equal to PL. And keep in mind in stat lab, it'll be actually probably be P1 equals P2, but for us, it's going to look like that. So there's your step 1. Step 2, did they give us alpha?
0.10.
I believe so. Yep, 0.10. And now step 3, we're gonna have to do a little bit of thinking because we don't actually have the data, but we've got enough. They told us, for instance, that with the vinyl gloves, I believe it was the vinyl gloves, let me just double check here. Yeah, the vinyl gloves had a 66% leak rate. So M sub V was 210 or 219, and 66% of those leaked. But I need an actual number here. I don't need 0.66, I need a number, the number of gloves that leaked. So how would I find that if I know that 66% of those leaked?
0.66 times 219.
Good, 0.66 times 219. If you pull out a calculator, that should give you 144.54. And I'll round that to the nearest integer. If you try putting this into statdisk, it's going to bark at you. It's going to say, no, I expect a nice whole number. And that would be the whole number. We'll do the same thing for latex gloves. 219 latex gloves, 15% of those leaked. And that turns into 32.85, which will round up to about 33. Let's put that into statdisk. First things first, I want to check the form of the alternative hypothesis, and that's wrong. I don't want P1 is less than P2. Which one of these three do I want?
The
1, 2, or
second
3? Second one, good. Now for the sample size, that was 219, of which 144 were successes or leaked. And then 219 again, this time only 33 leaked.
Significant 0-1.
Yeah, it's a highly significant result. P-value of 0.00000. There's virtually no chance you would get these results just by accident. So our p-value, thank you, is 0.0000.
You forgot to change the significance to 0.1.
That's
Oh.
what I mean.
Oh, okay. I'm sorry. That is what you said. Sorry. Does that change our decision? Actually, no, that's still wrong, isn't it? But it's not going to change our decision. So the significance level is 0.1. Even if I made the significance level 0.01, what's going to be our decision?
Reject H naught.
Yeah, reject H naught. It's not even close. I mean, nothing but zeros here. In fact, I think statdisk gave you 5 zeros. Nothing but zeros is going to be way less than any alpha that you typically use, either 0.1, 0.05, or 0.01. Still going to be less. So you're going to reject H naught. Step 6 is to state your conclusion in words. I guess the one thing that I wanted to point out here, and I'll let you worry about the state your conclusion stuff in words, is this last little bit here at the end. Now they gave you an 80% confidence interval. That's probably because we've got a one-sided alternative hypothesis. If you take that 0.1 and double it to get a two-sided alternative, that's why you're getting an 80%. Let me actually get a confidence interval for P1 minus P2. So I'm going to do that from this menu. Proportion to samples. I had 219 here, 145 here, 219 here, and 33 here. Here's my confidence interval. Somewhere between 0.43 and 0.589. But that's not the confidence interval for either one of these statistics. It's the confidence interval for P1 minus P2. Let's take a look at this. P1 minus P2. Now, when we do our confidence intervals and other calculations, a lot of times it's based on whether or not the null hypothesis is true. And the null hypothesis, the most basic form is that these two things are equal to each other, or that P1 equals P2. P1 equals P2. Now, if P1 equals P2, and I move that to the other side, what will I get? I'll get P1 minus P2 equals what? What's left here? I know this is algebra, sorry. If I move that to the other side, what's left here?
0.
0. So if the null hypothesis is true, then one of the values in your confidence interval should be 0. That should be possible if your confidence interval, or excuse me, if you're failing to reject the null hypothesis, then this should be one of the values from your confidence interval for P1 minus P2. Let's look at our confidence interval. Does this confidence interval contain 0? No,
It
0
does
is
not.
not in it. And what that's saying is that this is not a possibility, which means this is not a possibility. That can't be. But guess what? We rejected H0. We don't think that H0 is true. So if that's not true, then we're saying that P1 is different than P2. And your confidence interval shouldn't include 0. All right. That's a lot of little nuances stuff here at the end. We'll practice that some more this Monday, or excuse me, this Tuesday. We can do it Monday if you'd like to. We'll do it this Tuesday, and I'll actually apply it to the state of Michigan and how some of our different ethnic groups are dealing with the coronavirus. So we can look at that. A newly printed article from the Lancet on that stuff. Until then, any comments or thoughts to wrap this up here? All right. Well, let me stop things here.